All right, so let's get started. Welcome to everyone joining for the we've done enough now that I've lost count of what number talk this is to the Science by Diverse Sciences seminar series, a Cowbridge Physics and Astronomy seminar series, our very long and growing title. I'm very excited that this week we're welcoming Danny Caballero, who is at Michigan State University, where he's an associate professor in the Department of Physics and Astronomy. Danny got his BA at UT Austin in 2004. He's from Texas. Before going to Georgia Tech for graduate school, where he originally worked as an experimental physicist before shifting gears and essentially kind of starting up the physics education research program there at Georgia Tech. And from there, he went and did a postdoc at the University of Colorado Boulder with their physics education research group before moving to Michigan, where he's at now. A lot of his work is looking at either computation in physics education or using computational and data-driven methods to study STEM and physics education from a kind of a quantitative research standpoint. I also want to point out, Danny is are you one of the founders or just one of like the names I know from Pickup?
There are only two founders, so I'm not one of the founders. I'm just one of the worker bees.
Oh, okay. I don't know. I just you're the one I knew first, so I assumed you were. He's involved in something called Pickup, which is the Partnership for Implementation, yeah, of computation in undergraduate physics, which I can say as a faculty member, has been amazing to be on the learning side of all theirs. They're really involved in getting more computation into physics classrooms around the country. So let's give Danny a welcome, and he's going to be talking today about using data-driven discovery and quantitative methods for STEM education.
Thanks, Sarah. I hope everybody can see my slides. My computer just kind of shows me my slides, and that's sort of it. So, so in the upper right corner is a QR code, but also a link if you want a copy of the slides in PDF format for whatever reason. There may be things in there that you're interested in. I really appreciate folks inviting me to come talk with you today. When Sarah initially invited me, I said, sure, let's do November the 3rd. And I totally didn't realize what day that actually was at the time. So as usual, past Danny makes problems for present Danny. So let's see if this is gonna go, there we go. So the first thing I wanna do is just acknowledge the folks that do a lot of the work that I'm gonna talk about today. So I am one of the principal investigators of this group, the Learning Machines Lab, which is a group that works with quantitative data, mostly in STEM education, but exclusively in sort of higher education data sets. There's a few folks whose names and pictures will show up throughout who do a lot of this work, and without them and without their efforts, this work wouldn't get presented. So I want to acknowledge them up front. So you might ask the question, like, why focus on STEM education, right? I'm a physicist, as Sarah mentioned, and yet I work in STEM education. And I think for me, there's a lot of issues that I want to work on, but I don't have the expertise or the energy to work on them. But enabling other people to do it is really important to me. So there's certainly some global challenges that we have to deal with, like climate change, which is a major one that is affecting many of us, and especially those of y'all in California. Issues of information security, and how we actually secure networks and secure computer systems from different kinds of threats. The issue of renewable energy and how we deal with peak oil. Much of our energy is coming from non-renewable sources, and we need to figure out how to address those issues as we go forward, especially as energy consumption continues to go up. And something that I think we're all very familiar with at this point is how we handle disease outbreaks. I'm old enough to remember other disease outbreaks that occurred which did not take over the world in the way that COVID-19 has. And there are many sorts of policy and technological solutions that we need to address those kinds of things. In addition to these global challenges, there's advancements that we get sort of as a benefit from all of the work that people do around these issues. Um, one that's really close to me at MSU is multi-messenger astronomy. We look at lots of different ways of understanding and probing the universe. And most recently, this idea of understanding the universe through gravitational waves. Quantum computing, it's another big thing at MSU and other places where we can move from simple bits to superpositions of states to improve, cryptography and computing power. Bioinformatics, it's another huge area to understand the relationship between genes and things that we sort of observe in the everyday world at the macro level. And then extraterrestrial exploration, just another example of something that allows us to understand the universe around us. But these advances that we get in these technologies lead to many other sorts of consumer products and additional research that can be done. So there's no solutions to these global challenges or advances to these critical technologies without a high quality STEM education. It's part of what we need to do to achieve these goals. And so I work in that space of STEM education, which I'll say has existed for quite a while. There's many national documents that describe STEM education, starting with Rising Above the Gathering Storm is one of the more notable ones. Rising Above the Gathering Storm 2, which sort of expanded upon the prior publication. The Engage to Excel report, which came out during the Obama administration, that described the issues that we needed to address around STEM education and STEM teaching. And even most recently with the current administration, the Charting a Course for Success, America's Strategy for STEM Education. And I'll quote from that one because it's actually the most recent policy document, which talks about building strong foundations in STEM literacy, increasing diversity, equity, and inclusion in STEM, preparing the STEM workforce for the future. And if we translate these things to higher education, we must continually investigate the learning outcomes that we have in our courses and iteratively improve upon our instruction so that we continue to provide the best quality education that we can. We need to address the culture of STEM to increase recruitment and to better support retention. This comes from the need for more STEM graduates and more STEM teachers to continue the advances in technology and science that we lead on. And we need to modernize the curriculum and pedagogy to address these global challenges. And for me, this translates a lot over to thinking about computation, but could be a variety of other sorts of modernizations that you might think of. So I work in Michigan. I work in Michigan State, and Michigan State is a land grant institution. And I really believe in the land grant mission because I think that an institution that is responsible to the state and its citizens, and one that is the driver of advancement and the economy of the state is really important. I think a lot of that does flow from higher education. So if we look at STEM in Michigan, we find that many students in Michigan do not achieve proficiency in science and math at the middle and high school level. Students of color and those who are economically disadvantaged in our state are disproportionately affected. And this is something that, has a 2 or 3 times effect on these folks. Advanced STEM courses that we have are inaccessible to many of our students, particularly students of color and students in economically disadvantaged spaces. And few of our high school graduates demonstrate college readiness on the basis of reading and mathematics. And so we have a lot of work to do within the state of Michigan to prepare students for STEM programs. Those students who do enter 2-year colleges, few of them actually complete their degree programs. I believe at Michigan State, we have a graduation rate that's close to about 80% across all of our institution. But if you look at students who transfer from 2-year colleges, it's closer to about 50%. And so we need to think a lot about how we support those students as they make their transition from a 2-year college to a university like Michigan State. And as is well documented in many spaces, there are fewer women and people of color that earn STEM degrees than white and Asian men, and so STEM has an issue with the diversity of folks who are earning degrees in those programs. And as we are the land grant institution of MSU, or of Michigan, 75% of MSU students are Michiganders. They are from the state, and so the way that we address these issues, in the state of Michigan, is to address them throughout the STEM curriculum from K through 16. So in my department, we have these two twin goals of conducting original research and educating the next generation of Michigan citizens, basically. So on the left, you see a picture of students working at the National Superconducting Cyclotron Laboratory working on an experiment. And on the right, you see pictures from my colleague Vashti Sautel's Introductory Physics for the Life Sciences class, where students are making models of various systems. And my research couples these two together because I do research that can support education in STEM. And so the work that we do is really to understand a variety of things, including how students understand STEM concepts and practices and how their identity is shaped. We study curriculum and pedagogical effects. We look at how tools like mathematics or the computer support learning in different ways. We look at how contexts can affect that. And we have the same three spaces of research that most other research has as well, which is we draw on theory and we conduct experiments and we do applied work. And in particular, the group that I work within that I'm going to talk about today focuses on generating quantitative evidence for understanding issues in STEM education. So we are exclusively focused on these issues of quantitative education research. So this group was started from a project that my PhD student who just defended John Aiken and I worked on some years ago, where I was interested in understanding how students become physics majors. So this picture here is describing the entry point and the end point of a physics major at Michigan State. And what you see is that there are a lot of students who declare that they are a physics major when they start. And about half of those students end up earning a physics degree. So that is, of all the students that declare a physics major at some point in their career, only about half of them started and ended in physics. In fact, physics majors who start off in physics go on and earn degrees in a variety of fields, engineering, other STEM fields, non-STEM fields. And physics majors who earn physics degrees actually come from a lot of different spaces. And so the complexities of this degree earning was very interesting to us, but it was sort of something that we just started out looking at by trying to understand the entry point and the exit point. So one of the things that we became interested in was trying to analyze the data sort of in between. And this led us to think about the uses of machine learning and, which sort of leads to this picture here, right, of thinking about like artificial intelligence and all this other business, right? But it's much more straightforward than Hollywood would sort of have you believe. And it's also sort of less silly than XKCD would have you believe, where we just take all of the data that we're trying to understand and stick it into a model and stir it up. And if we don't like the answers that we get, we just continue to stir until we get the answers that we like. So I think in part this talk I want to sort of share with you how we think about machine learning in our work and then how we use it. So I'll start with just the premise of like the way that people often think about machine learning is that you have some data, you stick it into a machine, and you get results. And if that were the case, then we would publish significantly more papers than we do. But the way that we go about doing this is actually taking our data and we split it up into what's called a training set and a testing set. And that training set goes into a model. a model that is justified for the kind of problem that we're trying to solve. That could be linear regression. It could be as simple as that. It could be logistic regression, but it could be something more sophisticated like a random forest regressor or some sort of boosting method or something like that. But then what we end up doing is obtaining some sort of fit parameters to those data. So we get some information about how that model fits that data. Then we use those fit parameters to predict the output on the test data. So this is data that hasn't been seen by the model when it built up these fit parameters, and we predict the output that we would expect. And then from that, we can evaluate the model and say, well, how good did this model predict the output that we knew, right? So you can think of this as like, if you're trying to predict something like student grades, you might know the student's grades in the test data. You build a model, and then you have the model predict what the student's grades would be, and you compare the predicted grades to the actual grades to evaluate the quality of your model. So we don't just do that once, we do it a bunch of times. Could be 100 times, could be 10,000 times, because what we're doing there is building confidence in the model. We're trying to understand whether there are outlying models, because this process of using this training data is random in some sense, and the models that build it could also be randomized in some sense. And so you want to try to understand where there are good models and where there are not so good models in the way that you go about this approach. And so through that, we build some confidence, and we actually have some evaluation techniques that we can use to understand how good those models actually are. So in terms of a diagram that describes the kinds of problems that we solve, we tend to use supervised learning in the lab, simply because the kinds of data that we're interested in often have results that we are trying to build models of. What I mean by that is that we tend to have problems that we solve using classification, where we're trying to predict whether data is part of one class or another. Or we try to build a regression model where we are trying to understand the relationship between some features and some output. And I'm going to show you examples of both of those in a moment. We've done less unsupervised learning. I had an example of that from my dissertation work that I will share with you briefly, but it mostly comes from clustering, where we don't actually know the underlying structure of the data, but we try to find it by using techniques that look for similarity in some sense. And then there's some dimensional reduction techniques, things like a PCA or something like that, where you can take high dimensional data and reduce it down. In our work, we don't typically do that because the dimensionality of our data is not so high where it's necessary. We're not dealing with a million features to try to model some data. We're dealing with 10, 20, 30 features, something like that. So as education researchers, I think machine learning buys us a number of things, which I'll mention here. The data that we can have access to is increasingly complex in the sense that it talks about different aspects of the student's experience, whether those are various categories that the student puts themselves into, various pieces of information in terms of transactions that they have with a learning system. It could be things that they have registered in the registrar's office and so forth. And all of those data can be interconnected in different ways. And so, this data becomes larger than we've used in the past. It becomes relational in ways that we haven't seen in the past. And so these kinds of issues become really complicated because of the layers of the data and the relationships between them. The models that the data science provide us can actually handle a wider variety of data and predictions. So we can use all kinds of interesting data to ask different kinds of questions, and we can predict the output of a variety of kinds of things, like not just binary classes, but multi-class situations. And then the kinds of data that we can use doesn't have to all be numeric data. It can be categorical, it can be categorical and numeric, and so forth. The frameworks that data science uses to construct their models, develop and validate them, and so forth are pretty robust, and they're actually model agnostic for the most part, meaning that you can actually use multiple models that solve the same problem and evaluate those models. So I can use both a linear regression and a random forest regression and a support vector machine regression, and I can evaluate those basically in the same way to understand which ones are doing the best kind of work for me. This allows us to ask and answer some new research questions. I'll share some of those along the way. And in particular for our group, I'm interested in preparing students for 21st century careers as well. And in particular, the undergraduate students who are working in our lab, they're often not going to be education researchers. They're going to go off and do other stuff, but this kind of work prepares them to do research in machine learning. It prepares them to be data scientists. It prepares them for a wider variety of STEM careers than maybe I was able to offer them in the past. And so I think this allows us an opportunity to do some interesting things for students in terms of their future careers. A couple of caveats though: machine learning isn't always the right tool for the job. You know, sometimes just regular old analyses that we've used in the past are better for the questions that we have, and I'll show you some of that as well. And the interpretation of the results from machine learning models can be a challenge. Things that are more sophisticated, that involve more sophisticated algorithms, often are pretty closed box, in the sense that understanding what's going on underneath the hood and understanding how these features are leading to certain kinds of predictions are not really easy to do. So I'm going to walk you through just a couple of examples. I'll start with classification, where we're just trying to predict whether some data exists in one class or another. So this work is by my PhD student, Nick Young, who has been working on a wide variety of problems related to graduate education. So Nick was very interested in understanding whether a PhD applicant was admitted to a program. And so he used a technique that's rooted in what's called the decision tree, where you take some data, maybe the GPA, the GRE score, whether a student has research experience or whatnot, and you use those markers to understand whether an applicant was accepted into a program or not. And so these are just some examples. These are not real, just a cartoon here to show you that maybe if a student had a GPA over 3.0, they moved on to the next decision. Their GRE score was above 150. They moved on to the next decision. They had research experience, and then maybe they were accepted. So the way that Nick does this is he builds a lot of decision trees using a random forest. So it randomly grabs different data. In the data set, it randomly selects the different features, and it basically tries to predict whether the student was accepted or rejected from the program. And it uses basically the knowledge of a student being accepted or rejected, because we actually know that the applicant was accepted or rejected, to build the best possible model that it can. And we use a technique called an ROC curve to evaluate the quality of that model. So this ROC curve is basically showing you how good the model is at predicting true positives compares to false positives for different thresholds. And if you remove features from the model, you get closer to this diagonal line, which is the chance line, basically a 50-50 guess as to whether the person was admitted or not. And that tells you that the feature is potentially important. And more predictive means that the curve is fitting more towards the upper left-hand corner. So what Nick did was he ran this model on some data that we have at our institution, and he found that the top two predictive features were the student's physics GRE score and their undergraduate GPA. And all of the other features didn't really matter so much. And in fact, I think the next slide indicates to you that not only are these two features the most important, but that Nick was able to predict admissions with 75% accuracy with only those two pieces of data. So he could account for a significant admission probability with just those two pieces of information about the applicant. And this suggested to us, and we wrote about it in this paper, that these metric-heavy admissions can really limit the participation of women and folks of color in graduate physics programs. I have some slides later on to talk a little bit more about this in some detail if we have time to get to it. But it tends to be the case that women and folks of color earn lower physics GRE scores because the physics GRE is a biased assessment. And so by using those tools as metrics, we are certainly limiting the diversity of the pool of candidates and that are admitted to our programs. So as a second example, I'll tell you a little bit about a regression model. And this is rooted in some of the work that historically has been done in physics education research, where students who complete active learning courses tend to learn concepts more deeply. This was done in work, back in the 80s and then in the 90s. One of the most famous ones was conducted by Richard Hake, which showed that students in traditionally taught courses learned maybe about 25% of the concepts that they didn't already know, and students in active learning courses learned maybe more like 50%, so maybe twice the amount of learning, if you will, on a regularized assessment. And so one of the questions is really, why is that the case? And so one of my students who just recently defended his PhD, John Aiken, was really curious about how our mathematical models that we use to look at these impacts predict this kind of performance. So he asked the question, well, how does a student's school, the course that they take in their prior preparation, predict that performance? And so what John actually did is he built a simulated data set where he baked in the effect of prior preparation, that is, that students coming in with more physics understanding would earn higher scores at the end of the course. That the course that they took, whether it's traditional or transformed, would lead to higher performance by transformed courses, and that the school that they may attend may have a small effect. And so what you see on the left-hand side is the distribution of pretest scores. The three peaks actually represent three different types of schools based on his simulation. And on the right-hand side, you see the distribution of post-test scores, where the transformed courses indicate higher performance by students, or there's higher performance by students in those courses. So he built a model, and several models actually, using the standard techniques that we would use in regular quantitative STEM education research, a so-called ordinary least squares linear regression, where he's just trying to predict the outcome of the post-test score, and what's called a hierarchical linear model or mixed effects model, where he takes into account the relationship between the school and the course in his model, and then tries to predict the outcome. And what he found was that both of those techniques tended to fit the pretest scores a lot. And you can see that in the picture on the right, where the blue line and the black line are kind of overlapping each other. They don't overlap with the gray line, which is actually the true values he's trying to predict. And they end up with these three peaks because they're overfitting on the school variable. When he uses a technique called XGBoost, which is a boosted regression model, he finds that sort of effect goes away, and it actually does a much better job of controlling for those mixed effects in the model. So what John was doing here was basically showing that maybe some of these effects that we're seeing are not necessarily a result of the research we're doing, but a result of the methodologies that we're choosing to make our predictions. He has a more detailed paper that he's working on that describes this, but this was the work that he did for his thesis. He then tried to look at this with real data. So this is data that comes from the so-called LASSO system, which is this system that collects a lot of these tests for introductory physics courses. And so this is real pre-test and real post-test data. And what he found there is that the regular way that we would go about doing this, the ordinary least squares, again, the blue line, does a pretty poor job of fitting the real data, the gray line. And even the mixed effects model, the hierarchical linear model, doesn't do a great job either. The distribution doesn't quite follow the true values, but the gradient boosted model fits it pretty well. And he's done some statistical tests on those distributions to show that in fact, the gradient boosted prediction is statistically no different from the true values, whereas the distribution predicted by the mixed effects and the ordinary least squares fit is statistically different. So John's argument actually in his thesis is that there could be a lot of different good models that we need to use and we need to evaluate them, but that in his analysis that he found that prior preparation is the dominant predictor in all of his models, no matter how good they fit. So the last technique I'll show you about before we talk specifically about graduate admissions, because I think that's pretty interesting, is a clustering project that I did as part of my dissertation work, where what we did was we were giving students computational programs where they would solve these computational programs in Python in the laboratory every week. And then they would use those on their homework to solve new problems. And so they would be given a piece of code like this, which is meant to model the rotation of the Earth, sorry, not the rotation of the Earth, the moon moving around the Earth. And in the lab, they would make some changes to that code by adding different elements to it, by including a motion map, which is basically a stroboscopic image, a graph showing some separation. They would write the code for the integration loop, the forces, and so forth. So we did that with them quite a bit, about 15 times over the course of the semester. And so then we gave them a piece of code that they had never seen before and asked them to solve it individually. So they were given some central force problem. They had to assign the initial conditions, calculate the force, update the velocity, etc. And we found that about 60% of students were able to do that with no problem. But the interesting thing was actually the 40% or so that generated one or more errors in their code when they turned it in. And so we went through and classified those codes using a rubric where we marked up what the students did correctly or incorrectly on their code. And by doing that, we ended up with something like 117 or 125 different possible ways that students could have written their code incorrectly, which is way too many to understand what are the main issues that are associated with the code that they're writing. And so what you see here is what's called a dendrogram. It's basically a relationship illustrated by the distance between two students' pieces of code in terms of their score on this rubric. So it tells you like how close in terms of the score, the individual score they got on the rubric, one student's code is to another student's code. And so by doing this analysis, what you can see is that there's groupings of student codes that are quite similar to each other. And so using this technique of cluster analysis, we were able to uncover patterns in that data that found that actually 80% of student codes fell into just 5 clusters. Whoops. Sorry. Did my screen go away? Oh, can you see my screen again? Something happened there.
You're good.
Okay, good. Yeah, it just went away from me. So these 5 errors are things like the sign error in the force calculation, that the students had perfectly running code, but they made a typo in their initial conditions, and so on and so on. And so what we were able to do with that technique was be able to unpack the main message in terms of the kinds of error that a student made in their code. And without that clustering technique, it would have been very difficult to find those kinds of issues. Okay. All right. So I want to focus for a minute just because of the topic here on graduate admissions. And I want to talk a little bit about some of the issues that we have in graduate admissions in physics. So one of the first things that if you start looking into this is you see that the American Institute of Physics has collected a lot of information over the years on PhDs earned by folks. And you can see that all of the trend lines here in terms of the fraction of women that are earning PhDs are all trending upwards. But if you look at physics, which is the green line, you find that, you know, about 20% of our the PhDs that we grant every year are to women, 80% are to men. If we look at African Americans and Hispanic Americans, we're no longer counting the percentage of folks, we're actually counting individual people on a 2-year rolling average. So the year that I earned my PhD, there were about 12 or 13 other Hispanic Americans that earned PhDs in physics in that year. And so there's a challenge here for physics, which is to think about the way that we diversify the graduate student population and the undergraduate population, and also how we support those folks to fruitful scientific careers. So to get us all on the same page, I want to talk a little bit about my department and our goals. So one of the first goals that we have had is to increase the proportion of underrepresented folks in our graduate physics program and support their transition to professional careers. Another is to create structures that remove the barriers or promote full participation of those folks in our program. And the third is to reshape the culture of our department to bring traditionally excluded folks into critical activities that we engage in and decision-making of the department. And so to center us a little bit, I want to talk a little bit about DEI, which is the acronym for diversity, equity, and inclusion. I've borrowed these definitions from Berkeley, but I think they're familiar to a number of folks. So when I think about diversity, I think about the different identities that people hold at the same time. You know, those identities can be race, ethnicity, gender expression, etc. When I think about equity, I think about the guarantee of fair treatment and access, opportunity, and advancement for folks, and striving to identify and eliminate barriers that prevent full participation. And when we think about inclusion, what I'm thinking about there is how we bring in people who have been traditionally excluded into the activities and decision-making that we have going on, and sharing power to ensure equal access to those opportunities and resources. Now, the reason I want to sort of separate these two out is because they're often talked about together, and there are 3 different ideas. And the ways in which we go to address each of them is different. So I'm going to talk a little bit more about diversity and a little bit about equity with regard to graduate admissions, but I won't talk about the other things because there's a lot more work that we have to do. So when we think about this in graduate physics education, we might think of diversity as working to change the representation of applicants that are admitted to our program by engaging in some active recruiting, either through at the SACNAS meeting or the National Society of Black Physicists meeting, for example. When I think about equity, right, I think about changing the admissions criteria to remove barriers for applicants and creating structures that support their transition to graduate physics programs like the APS Bridge program. When I think about inclusion, I think about we might create governance structures where graduate students, you know, vote on departmental decisions and implementing a code of conduct with accountability practices, right? These are important things that we can think about. So let's talk a little bit about admissions, right? So if we look at the numerical markers that are used for admission, what we see is that the distribution of GRE scores is different depending on the group that we're looking at. So white and Asian applicants earn higher GRE scores than Hispanic and Black applicants. Male applicants tend to earn higher GRE scores than female applicants. But if we use those markers for admission and we then try to translate that over to the completion probability in terms of a PhD, we find that those aren't really factors. This is work done by Casey Miller and his colleagues in this Science Advances paper from 2019. And so even though we use these numerical markers, they're actually not predictive of earning a PhD. And students are aware of the biases in the GRE. And some of them, as reported by Cochran and Wilson, see that GRE is a barrier to even bothering to apply to graduate programs in the first place. You know, what the GRE folks say, the ETS says, is that subject tests can help you stand out from other applicants. And so Nick, my PhD student, investigated this, looking at 5 different graduate programs across the country, and found that, you know, scoring highly on the physics jury doesn't really help applicants from smaller or less selective schools stand out. They still pick folks predominantly with high GRE scores and high GPAs. And he did an analysis, what's called a mediation analysis, to look at that in some detail, and found that, physics GRE scores explain some of the differences in admission probability based on an applicant's undergraduate institution, but we really need more data to understand this better. This paper is on the archive, and it's been submitted if you want to dig into it in more detail. So if we look at Michigan State as a case, we're just a traditional physics department. There's nothing super special about us. We're a large physics program like many other large physics programs across the country. We have a lot of faculty and teaching staff. We have about 200 graduate students. We have about 300 applicants per year. We admit about 60 of those applicants, and about half of those applicants actually start at MSU. That's because they may choose to do other things or go to other programs. So we're just a large high research activity program, in part because of the nuclear physics facility we have across the street. So our admissions process prior to 2018 was pretty standard. It was like any other admissions process that you see across the country. Applicants submitted transcripts, scores, statements, letters, etc. The spreadsheets were organized their materials, a large committee reviewed them. We used soft cutoffs for the GRE to determine admissions, and this is a common practice across many institutions. And we found that in the fall of 2017, about 15% of the applicants that we admitted were women, and about 7% identified as being a racial or ethnic minority. Prior to 2017, we didn't even collect that information, which suggests how much on the mind of the Graduate Admissions Committee diversity was. And as I'll remind you, we can predict basically 80% of the admitted students with just their GRE score and their undergraduate GPA. That actually comes from this data. So one of the other things is that if we look at those GRE cutoffs, Nils Mikkelsen, an undergraduate student who works with Nick and I, looked at those GRE cutoffs and found that they favor students with high GPAs, students from large schools, and male students. And that's kind of regardless of the GRE cutoff. What you're seeing here is a graph of the importance of a feature in a machine learning model called conditional interference forest, which shows that the most predictive feature is the undergraduate GPA, the next most is the gender of the applicant, and then the third most is the number of PhD graduates, which is a proxy for how big the school is that they came from. And regardless of the cutoff that's used, those are the top three features. So with this data, we talked to our graduate admissions folks, and we talked to a bunch of different faculty to try to make some changes to this process. In the fall of 2017, Julie Passelt, who's at USC, delivered a colloquium on graduate admissions to our department. And with Casey Miller, who's at RIT, they ran a workshop on developing graduate admissions rubrics. And so the graduate program committee developed a rubric to evaluate applicants in a different way than we had done in the past. And in the spring of 2018, we had our first class of students admitted using that rubric. So since 2018, we've used a rubric that looks at students' academic preparation, their coursework, their grades or honors, that's about 25%. Looks at their research experience, the quality of work that they have engaged in, the kinds of skills that they developed. It looks at non-cognitive competencies, which is a big part of what Julie and Casey talk about in terms of evaluating candidates, their conscientiousness, their initiative, their perseverance, how the student fits with the program, the research field, the needs of our groups, the advocacy for diversity that we have as a department. And then their GRE scores are still counted, but a very small fraction. And so when we made that change, we found that year over year, we've increased the number of admitted students who are women and the number of admitted students who are who identify as a racial or ethnic minority, to the point that last year, 35% of our admitted students were women and 15% were students who identified as a racial or ethnic minority, in contrast to 15 and 7% in the fall of 2017. So I'm not telling you that we've certainly solved the problem. There's a lot of work to do, our first year experience needs to be retooled because we are admitting students on different criteria than before. So we need to focus on the transition to graduate school for those students. The pathways to PhD candidacy needs to be addressed because at the moment, PhD candidacy is admitted based on grades and courses only. And these students, again, are being admitted on a wider variety of criteria. And so our candidacy requirements should reflect that diversity. We are working to address the issues of systemic racism and sexism throughout our program. A really interesting paper by Aycock et al. Talks about the experiences of women in physics conferences, and it's certainly informed the kinds of work that we're trying to do. And recently we joined the APS Ideas group, the Inclusion, Diversity, and Equity Alliance, to try to better understand ways that different departments are addressing these issues and how we go about doing it ourselves. So just a couple takeaways from this particular project. You know, the traditional metrics that we use for admissions do not align with diversity goals, and they don't predict the completion of PhD programs. The GRE does not help students stand out, and the cutoffs, even soft ones, are problematic. Admissions rubrics, like we've used them, codify what we value, and they can help increase diversity. But there's still a lot of work that we have to do regarding equity and inclusivity, particularly in our graduate programs, but across all of our work. So I'll end with sort of where I began. Machine learning buys us as education researchers a wider variety of things. You know, the data we have access to is increasingly complicated, and we have to deal with that. The models that we have can handle a wider variety of data and predictions. The frameworks that we use are more robust in terms of the way we can develop and validate models. We begin to ask and answer new questions in our research, and we're better preparing students for 21st century careers. So I think quantitative STEM ed has to engage in machine learning and explore its uses and acknowledge that we have a lot to learn. So the work that I do connects the twin goals of my department in terms of conducting original research and educating the next generation. And I try to do research that can support educational goals. I'm not able to do that without a community of support. And so I want to show you the folks that I get to work with every day, although I haven't gotten to see them in person for quite a long time, but they're very important to me. So thank you very much.
All right, thank you very much for a great talk. As I say, I don't know how much you know about Calbridge's mission, but you talking about the applying this to graduate admissions is basically like the most perfect topic you could have talked about with Calbridge.
Cool.
Because that's actually been one of the big fights. This is a bridge. It's CSU to UC bridge program, but one of the big fights is getting recognition. Sorry, my dog. Maybe Sarah, take that.
I was gonna say, while Sarah mutes herself because her dogs are barking probably at the pool guy or something. Julie actually is one of our researchers, so we are deeply involved with her, and so she's using us as a test bed for other future research also. I had a question. So you talked a lot about predictors of getting into graduate school, which is one part of the step, and you mentioned towards the end, but I don't remember seeing anything specific. What are some of the big predictors of success in graduate school? Because that seems like what we should actually be focusing on when we focus on admissions to graduate school.
Yeah, that's a great question. I think some of that work is ongoing. So if you look at Casey's paper, they're using the things that we admit on to determine basically whether people are earning their PhDs or not. I think the thing that I've seen most often come up is performance in first year courses. But that also might be a proxy for the candidacy, right? So like at MSU, if you don't earn high grades in your first year courses, you're not admitted to candidacy. So, right, like you're sort of using the the candidacy conditions as a conditions for moving on to the next thing, right? And so one of the things, like, I get, yeah, so sorry, Carol, I'm just like circulating around your question, right? I guess the answer to your question is, I don't really know, but it's all sort of intersecting with like what the specific requirements are for admission to candidacy at that program. And the programs that are typically represented use some proxy of first year performance to be admitted to candidacy. So first year performance becomes the thing that determines PhD completion, because you have to get through the candidacy piece and collecting more information on students like after they finish their first year programs. Like there's not easy things to collect, right? Because it's less about classes and things like that. One of the things that I think we're working on, just to like, and then I'll button it up, right? Is we're trying to understand diverse pathways for candidacy, right? Because if we're starting to admit students on a wider variety of criteria, and we value something different than we have in the past, which traditionally we valued high GRE scores and high undergraduate GPAs, then what we should do is provide pathways for candidates based on those values. So based on their research productivity, based on their relationship to the department broadly, you know, et cetera. So I think we got to think about those things.
Okay, and we have a couple of questions in our Q&A, and there's more popping in, and we have someone who's raised their hand also. So if you've raised your hand, if you could pop your question into the Q&A, that would be useful. And Danny, if you can see the Q&A, feel free to pick whatever entices you, because we now have quite a few.
Yeah, I'm reading them now, so let me see here.
And if you could just read aloud whichever one you decide.
Oh yeah, sorry. So I'm reading Arlette's question about given prior preparation is the main indicator of post-test scores, and students of color tend to be less prepared. Is it possible to have the same GPA in physics classes for students of color and others? GPA is important for graduate admissions, as you indicate. What grading techniques do you suggest? In my experience, students of color have less time available to study. Yeah, I think so. Arlette's question is a really good one. In this, so like I want to disentangle a little bit of like the markers that we use to evaluate students, which are like GPAs, and then the ways that we best support them, which I think is part of her second question. And so like one of the things that I think is really problematic about many of the courses that we often teach is that the grades are often competitive. So a lot of times grading will be done in a way that allows a certain fraction of students to be in certain kinds of grade levels, right? So like you'll say like maybe 10% of the students can earn a 4 and 20% can earn a 3.5. What that does is it creates a competition structure that students do not participate in a way that allows them to learn and achieve their best performance, right? Because if I'm trying to get that 4, I might not be incentivized to support other students in class learning, because if I help them, then I'm not going to be the 4 student. I'm going to be competing with them to be the 4 student. And so I think grading structures that reward collaboration, that reward growth, are the kinds of ones that we should be trying to embrace, because those are the ones that demonstrate student achievement in a way that sort of aligns with like a longer term learner, right? Someone who's going to be learning in a research environment, someone who's going to be learning from other people and supporting the learning of other people. So that's sort of my comment that I have on that. Should I keep going through these questions? Yeah, okay. So Thomas asks, if there's a rubric, can it be gained by the students? Those who have a bit of information about the rubric, can they do better, or would the rubric be bulletproof? I guess so when we developed the rubric, I actually wanted to give the rubric to students because I thought it was important for them to know what we evaluated them on. That doesn't mean that we are specific about like how we score the thing. Like we wouldn't release that, but we could say like, oh, well, we are looking for these kinds of things. I think the question of whether a student is gaming it or not, you know, that's a possibility, because people could be incentivized to do that. But I do think it's important to let students know that we are looking at different things. In particular, when you think about the work that Geraldine Cochran and oh my gosh, I can't remember the first name, but and then Wilson did about the GRE being a barrier for students to even apply, right? If you're more forthcoming about how you're evaluating them, they may recognize that actually they do belong in a graduate program and that they can apply to it. John asks, oh, hi, John. What specific things do you plan to address for the new PhD students in the transition to graduate school piece? That's a great question. So one of the things that we've noticed just is that we have more applicants that are applying from smaller institutions that may have less opportunity to take undergraduate coursework that we would expect. So for example, we have admitted quite a number of students that have never taken statistical mechanics, for example. And they are expected to take graduate statistical mechanics. So we have to think about how we support those students when they start here so that they are prepared to take graduate statistical mechanics. So what we have been doing is allocating or we've been allowing those students to take undergraduate courses at MSU by talking with them and saying like, hey, this is the course that we're expecting you to take. Your transcript shows that you have these courses. Would you be comfortable taking this undergraduate course in StatMech prior to taking the graduate course? And part of that is like inviting them to take those courses as a support system, but the other part of it is acknowledging that we are going to commit funds to that student to be a teaching assistant for that semester while they're taking that course, because we want to support them through it, right? So part of it is both the signaling that we're there to support them through the academic piece. The other is the financial piece, that we're not going to like revoke any sort of funding for them when they're taking maybe some coursework that they hadn't taken. So Eric asks, are you looking at how successful your own undergraduates are getting into graduate school and what interventions there might be there? I will say, like, my understanding of the number of undergraduates at MSU that get into graduate programs is low compared to the national average. The national average is somewhere around 45 or 50%. MSU is closer to 25%. And in part, that's because I think students tend to go into other things here in Michigan, and they don't choose to go to graduate school. So we haven't really spent a lot of time on that. We have been talking about general career preparation and trying to build a seminar course that students take once every year that prepares them for professional stuff, because we don't actually have any sort of thing like that where we're talking about like physics as a meta thing, where it's like, what are all the opportunities that are available to you? What are things that you should be aware of? Like, when should you be applying for REUs? When should you be thinking about a teaching certificate? So we've been talking about essentially a ride along course for our majors that prepares them generally for physics as a career. So Carissa asks, since you moved to machine learning models, have there been any biases that showed up in your results that you've had to correct for? Yes, absolutely. So there are interesting biases that come in with different models, where if you're looking at the things that I showed you about feature importances, where you're trying to figure out which things are the most productive for evaluating the quality of your model, sometimes it can be simply because the feature has a wide bandwidth, meaning that a feature that is binary compared to a feature that has like 10 categories compared to a feature that is on a numerical scale will just simply be more important because of the way the model works. And so you have to be, sorry, my kids are jumping upstairs and you're probably hearing some of that, or they're dancing or something. Sorry. So yeah, I guess the answer is yes. Yes, there are biases. That's why we use a multiplicity of models, because we try to evaluate a variety of models to see where those biases are and understand if they're present because of the algorithm or if they're present because of the data or where it's coming from. Oh my gosh, there's a lot of questions. So Eric asks, do you have some feeling for how much of undergraduate student success is baked in at high school and how important adventures are there? That's a great question, Eric. I think so there's two ways to answer your question. One is I do think that that's the case, that we have to think about the whole system, because we can't imagine that the higher education system is closed. It's certainly not, right? Because the students that we get come from high school, but the students that we train to be teachers come from our programs, right? And so that whole system and that whole structure is interrelated. And so that's really important. The other thing is that in some sense, you can be agnostic about that. The students that you have coming into your program are the students you have coming into your program, right? And you have to best support those students as they come into your program. And so I think both of those issues of doing the best job you can to support the students that are coming into the program while also trying to affect the larger system. Those are the, I think, twin parts of what have to be done.
One quick thing to that I want to point out, I don't know how many of you read the APS News. This month's back page was actually by Carl Wyman, exactly on that, looking at how physics preparation in high school kind of sets often who's successful in university level physics, especially intro level, and it's kind of a bit of a call for action to look at these exact things. So I just wanted to point that out, that if you need to convince anyone, you get your Nobel Prize winner that does physics education research writing about this. So it's a good article to send around. Oh my gosh, the questions keep rolling in. We may have time for one or two more, depending on how long you feel like answering questions.
Yeah, I'm happy. I mean, there's two more here that I see. I don't know if you see others.
One is also Brandon just saying hi.
Oh, okay. Hi, Brandon. So Lynn asks about a graduate program that gave a diagnostic test after entry to help decide what courses you should take at first, and have we tried that approach? And the answer is actually yes. That's what we used to do. We had an exam that we gave students in the first week before they started, and we used that as a placement tool. We've actually stopped using it, and the reason we stopped using it is because the graduate program coordinator could identify where students might need to have gaps shorn up by just looking at their transcript. And so there was a discussion about should the first thing that these graduate students do when they come to our program is take an exam, and we decided that that wasn't useful or as useful. And so what we've done instead is look at the transcripts, and the graduate admissions person meets with every student, and for students where he's identified that they might benefit from this, he talks with them individually about it, and more often than not they choose to take the undergraduate course. And we haven't found much difference in when we use the exam and when we haven't used the exam in terms of students' first year experience. So it was also a huge pain because we had to write the questions and grade it, and grade it quickly because it had to be returned to the students so they could register. It was a lot of overhead. Okay, and then so Brandon asks, more broadly, does this help? So I guess, has this helped you, and how has this helped you rethink the structure of the undergraduate program and how you prepare students for whatever career they pursue, right? So Brandon's asking, how does the work that we've done make us think about the undergraduate program? And I think part of the answer to that question is we don't really do a good job with professional preparation for our students. We're doing a pretty good job academically in terms of the coursework that they're taking to be prepared for a graduate program, but we're not really thinking about the 80% of students or the 75% of students that don't go on to graduate programs. And so we are now thinking about those students. We are thinking about different particular ways that we could have the undergraduate program structured to lead them to different careers, and also how we can mentor them all the way along into different kinds of careers in physics, whether those are careers that involve graduate programs, whether those are careers that are STEM related, whether those are careers that are teaching related, whether they are industry, etc. So we need to do a better job of of constructing our undergraduate program to mentor students all the way along. And that's one of the things that this has really helped us to do, is to think about how we're going to be doing that. So
I think we managed to get through them all. Thank you so much. I'm going to end on, why is the GRE still worth 10% if the GRE is like a biased instrument that doesn't really have predictive power, and a lot of universities are starting to get rid of it?
yeah, because I work at a traditional physics department with 68 faculty, most of who believe it's still a tool. So, I mean, I think we're not using it this year for sure, as most graduate programs are not using it because of COVID and students can't take it. I imagine we're probably not going to use it next year because there's going to be a backlog of graduate applicants. And this is a time when we are thinking very, like it's a very opportune time to actually just get rid of it entirely. Because if we admit 2 years worth of applicants without it, then what's really the point anymore?
That's kind of what I'm hoping departments will trend towards, of like, we did fine without it for a while. So I'm hoping it's a bit of a turning point there.
Me too.
Yeah. Well, thank you very, very much for coming and talk. I don't know if you had a little time, if any students are around and wanted to chat. Sometimes we offer time to, like, meet in small groups.
Yeah, I'm happy to hang out a little bit.
If you're around, just hang out. Usually we'll switch to like a smaller Zoom channel. That way on the webinar, it can be weird to bring everyone as panelists. So if any students want to stick around and chat for a few minutes, I will pop a link to another Zoom meeting that we can go to chat. If not, I thank you all for attending today. But I still see a bunch of people in the attendance, so I'll wait a few minutes and I'll pop that link in the chat right now. I believe I can send this to all attendees. If you're a student and want to chat with Danny for a little bit, there's a link we can all hop over to.
I should leave this then, Sarah?
Yeah.